And
would you like to say anything?
Maybe I say just a few words. So I think many of us in this room know Grégory because of his outstanding achievements in probability. His area of research is random planar maps. This is what he's going to tell us about, I'm sure. And so he's very well known in the field for his groundbreaking proof of the fact that uniform planar maps rescale to the Brownian map in the scaling limit, which is something that was proved, I think, in 2011. Is that correct? Yeah. So he's received already many awards for this, in particular the prize from the European Mathematical Society in 2012. And so we are very grateful that he's accepted to come and spend a month here at the Newton Institute for this program. And
all the pleasure is for me, in fact.
Thank you very much.
Thanks a lot. Again, I mean, it's really all the pleasure is for me. It's the second time already since my visit, the beginning of my visit here in January, that I have the opportunity to thank the organizers of this random geometry program, and in particular Nathanael. I'm very grateful to have been given this fellowship of the Rothschild Foundation. So it's really a great pleasure for me to to do this seminar on random maps and two-dimensional random geometries. So I was told to stay at a level for a general audience of mathematicians. So that's really the spirit in which I've been preparing this talk. So when I see the public, though, it seems to me that there are a very large proportion of people who are if not specialists of the topic, at least a very prominent probabilists. So so I should maybe apologize to a proportion of you who already probably know these things quite well. But since also, as we were told, that this is a recorded seminar, I think I will really keep a kind of slow pace for people who want to see this talk online. So, okay, so what is this topic about? So the motivating question for this talk and this problem in general is the following naive question, which is if you consider the two-dimensional sphere, the usual round sphere, but decide to equip this sphere with a metric structure which is completely random, then what does this sphere look like? Okay, and by metric, of course, the natural notion of metric that you can decide to choose is a Riemannian metric. Okay, but then in this case, it doesn't really quite make sense to choose such a metric, at random, and also it is completely at random. Means maybe in a uniform way. And the problem, of course, is that the set of Riemannian metrics on the sphere is an infinite dimensional set in which there is no natural uniform or Lebesgue measure. Okay. So you want to maybe to compare this question to another seemingly simpler question, which is what does a continuous function, a continuous path in RD look like if it's chosen completely at random? Okay. It's a kind of one-dimensional analog of this initial question, and maybe it doesn't look much simpler, but at least there is a natural, for people doing probability, it's quite natural that the answer to this question should be Brownian motion, and there are many reasons why Brownian motion should be indeed a continuous function chosen at random, say uniformly at random. And one of the ways to make sense of this is to in fact replace these functions by discretized versions of functions. And the discretized continuous function is random function is really a random walk, or say a discrete random lattice path in RD. And in this case, completely at random makes more sense. So the easiest natural model that you can think about is simple random walk in RD. So you consider a sequence of uniform random variables among either the vectors of the canonical basis of RD or their opposites. Okay, and you choose such a psi n uniformly at random with probability 1/2D. Okay, And then you consider the sum of these increments, okay? And then you obtain, of course, the simple random walk in Rd. And Sn is just going to be the position in Rd of the walker at time n. And here is, for instance, a trajectory of the random walk started at the point 0, which is around here, and then does something like this. And after a time, after a long time, after maybe 30,000, it's around here. Okay. Then, of course, one of the first things you learn in probability theory is what is approximately the location of the walker at time n for n large. Okay, and so what's the result behind that? It's really the central limit theorem, which tells you that when you rescale this sum of independent random variables with a finite covariance matrix, then this rescaled object converges in distribution to a Gaussian random variable in Rd, standard Gaussian variable in Rd. So it's a result really of probabilistic nature. It doesn't tell you that there is an almost sure limit for this sequence. It's not like the law of large number. Of course, the law of large numbers will tell you that Sn over n is going to converge to 0, which is consistent with this result. But this is really a final result that tells you that the probability that the walk at time n is inside a little ball is given by the probability that this standard Gaussian variable is in the same ball. It's really the content of this result. Okay? And of course, you can make this result even more precise, because this result tells you only an information about the position of the walk at a given time. But if you want to consider a functional limit theorem, you want really to consider the walk as a random function. And as a function, it's going to converge in distribution to an object, which is called Brownian motion, of course. And how do you characterize the limiting object? Well, simply from the fact that we already know that the marginal distributions, namely the law of Bt for any given time t, has to be Gaussian. It's given again by the central limit theorem. But also the increments of Bt should be independent random variables, because the same property is true in the discrete picture. Okay, the increments of the random walk between time 0 and S and t are independent random variables, because between S and t you just sum random variables that are independent from the ns first one, say. Okay. Therefore, you can, in fact, you can improve a little bit on what I've just said and prove a really functional limit theorem, namely that you have a convergence of distribution of this seen as a random function to Brownian motion for the topology of uniform convergence over compact subsets of R+, okay, the time interval. Okay. And that's, a way to see Brownian motion as a scaling limit, of course, of random walks. But the strength of this result, I mean, the strength maybe of the limiting object is really its universal aspects, because if you decide to replace the steps of the random walk, which were just nearest neighbor steps, by steps psi1, psi2, and so on, which are independent and have the same distribution with a covariance matrix equal to the identity of Rd, so you want to have this isotropy condition, then the limiting distribution is going to be always Brownian motion. Okay, so Brownian motion does not really depend on the nature of the discretization that you've chosen. Okay, so it's called the universality of Brownian motion, and of course it's one of the most important features of Brownian motion. So with this in mind, we can come back to our original question and try to attack this question of defining random metrics on the two-dimensional sphere by a discretization approach. Okay? And it turns out that the natural two-dimensional analog of random walks are maps. Okay? So what is a map? A map is just a graph which is embedded in the sphere in a proper way. Namely, two edges of the graph are not allowed to cross except maybe at their endpoints, okay, which are vertices adjacent to these edges. Okay? And I really want to consider graphs which are a priori not simple graphs, they are really multi-graphs, so you have loops or multiple edges that are allowed. And for now, I want these graphs to be finite and connected. Okay? And so for technical reasons, it's often useful to consider rooted maps. It's a way to, if you like, break the symmetries or to cancel the symmetries of the map So a rooted map, a root in a map, if you like, is a distinguished oriented edge. Okay, for instance, this one. And I want to call a face of a map a connected component of the complement of the embedding. Okay, so a face is the faces are the regions which are left in white in this picture, if you like. And of course, the degree of this of a face is the number of edges that it's incident to. Okay, for instance, here this is really a face of degree 4 or a quadrangle. Okay, so this is the definition of a map, and I really want to consider maps as combinatorial objects. Namely, in the previous definition, of course, there is a huge uncountable family of maps. Okay, even an edge has uncountably many ways to be embedded as a simple curve in the sphere. But then I want to consider that two maps which really represent the same combinatorial object, if you like, the same embedded graph up to homeomorphisms of the surface that I'm of the sphere are really the same object. So again, I want to identify embeddings of graphs which differ by an orientation preserving homeomorphism of the underlying surface, namely the sphere. So these two are really the same map, although they are different embeddings. And here, just this edge has been slightly distorted inside this face. So nothing bad. However, these two maps, which are the same, are different from that one. And the reason for that is a simple degree counting argument. Okay, the degree of this face here is 3 in the 3 picture, no problem. And the degree of that face here is really 6 because you have 6 incident edges to this face with this edge counted twice because when you go around you count it twice. Okay, and here so you have a face of degree 6 and the outer face here has degree 5. Okay, here in this picture things are different. This face has degree 4 and the outer face has degree 7. Okay, because again this edge is counted twice. So definitely these two maps cannot be the same because the face degrees is something that is preserved under isomorphisms of maps. Okay, and once you've done that, maps become a combinatorial family, and you can try to count them. And in particular, it was proved by Tutt in the 60s that if you consider the set of all rooted maps with n edges, okay, and considered again up to isometry, then the number of such maps is given by this very simple formula, which is, here you can recognize a Catalan number 1 over n plus 1, 2n choose n, and then a prefactor 3 to the n times 2 over n plus 2. Okay, so a very, very simple formula. And as you might know, Catalan numbers here actually enumerate plane trees with n edges, and this is not a coincidence, and we will see later where trees come in the picture. Okay, so here are a couple of simulations of large random maps, because again, let us think about a random map as a discretized version of a metric sphere, if you like. And if we want to obtain a continuum version for that, we need to take very large random maps. And a natural thing to do is to consider a particular family of maps, for instance, quadrangulation of the sphere, meaning maps in which all the faces have degree 4. Okay? And consider one such quadrangulation with, say, a fixed number of faces, maybe 30,000 plus 2. And consider one of them uniformly at random. And when you do that, you obtain pictures like that. So of course, this embedding of the map, so a simulation which was done by Jean-François Marquer, is not at all an isometric embedding, but at least it's done in such a way that vertices that are close in the graph are also close in the embedding of the graph in the 3 space. So really, you should think about this embedding as being in the 3 space. Okay, and you see that some structure of a random geometry does appear, which keeps a little bit the flavor, if you like, of a random surface, even though it's definitely something which has a very wild geometry. So here is another simulation, this one by Nicolas Curien, which emphasizes more the role of the faces. So I think it's really a random quadrangulation, although the faces look like triangles. the idea is that in a quadrangulation you can decide to draw the diagonals, or at least one diagonal inside each square, and you obtain a triangulation. And I think it's probably the embedding that we see here. Okay. And here is another simulation by Guillaume Chapuis of a random quadrangulation, this time on a different surface than the sphere, because there is nothing really special to the sphere, although the theory that I'm going to present is easier to see on the sphere. And well, I didn't include them, but there are also, many people have been doing simulations of random maps, and I invite you to have a look at the web page of Jérémy Bettinelli, who has done really a nice rotating embeddings of these maps with topologies that are much more general than this one. Okay, so now the first questions you can ask about these objects is, what is the metric which is induced by such random objects? Okay, so again, to formalize things a little bit, I've denoted by Qn a uniform random variable in the set Qn of rooted plane quadrangulations with n faces, and you should imagine n to be large. Once you have such an object, there are many ways to see them as endowing the sphere with a metric, and one possible way is to view the quadrangulation as the associated Riemannian surface, if you like, in which all the quadrangles in the map are really unit squares, unit Euclidean squares that are glued together, okay, according to the structure of the map. And this will endow the resulting surface, which is the topological sphere, with a metric which is flat everywhere except maybe at the vertices, which can be conical singularities. Okay? And this surface comes with a metric, and that's one way to endow a map with a metric. But in this situation, I will consider a simpler metric for my purpose, which is just the discrete graph distance in the map. Okay? So the set of vertices of the map Qn is endowed with the graph distance dqn, where the distance between two vertices u and v is the length of the minimal, the minimal number of edges that you need to go from u to v. Okay? And then an important result by Chassin and Schaeffer, which first appeared in 2002 and was published 2 years later, shows that the typical, distance dqn between u and v. So you should think about u and v as being 2 points in this map being chosen uniformly at random. Then the typical distance should scale like n to the power 1/4 as n goes to infinity. Okay, and they of course obtained a more refined result. But at least it tells you that for typical points inside this map, you need of order n to the 1/4 edges to go from one vertex to the other. Okay. So this asks, of course, what happens when you rescale this graph distance by n to the 1/4. And the main theorem here is the following. So again, you consider your uniform random quadrangulation and consider and put on it the graph distance rescaled by n to the minus 1/4, okay, in order that these distances now become of order 1 as n goes to infinity. And there is also a little prefactor 8/9, which appears here for reasons of renormalizations that are really not relevant for this particular talk here. And this object, which is now a finite random metric space, converges in distribution as n goes to infinity to a limiting random metric space SD, which is called the Brownian map. Okay? And this convergence in distribution holds for the so-called Gromov-Hausdorff topology on the family of metric spaces seen up to isometries. Okay? So I won't be too precise about what it means for a sequence of metric spaces to converge in this topology, but you should really think of the Gromov-Hausdorff topology as a kind of elaborate, improved version of the Hausdorff convergence. So it's well known that in essentially any metric space, there is a topology on the closed subsets of this metric space, which is can be metrized by the Hausdorff distance, which tells you measures distances between closed subsets, if you like. And for abstract metric spaces xn and x, you say that xn converges to x for the Gromov-Hausdorff topology if you can find some embedding of xn and x in some common big metric space, in such a way that these embeddings x prime n converge to x prime in the Hausdorff topology in this larger space. Okay, so it's actually this actually defines at least the notion of convergence, but this notion of convergence corresponds really to a topology on the set of metric spaces, or at least compact metric spaces, seen up to isometry. Okay, of course, two metric spaces that are the same up to isometry, are not distinguished by this Gromov-Hausdorff topology. Okay. So I mentioned that this result has been proved in 2011 by independent approaches by Jean-François Le Gall and myself, and in fact, this was really the last, if you like, stone in a long story that started with the work by Chassin and Schaeffer about convergence of these metric spaces. And I indicated that before this work, the convergence was only known up to extraction of subsequences. Okay, so if you like, there was a result about relative compactness for the laws of these objects, but no uniqueness. Okay, so this theorem of 2011 really is something about the uniqueness of the limiting space. So I want to tell you a couple of results of properties that are satisfied by this limiting space that is going to connect the discussion to the question that we asked in the beginning. Okay? So the first property is that this limiting space is indeed a two-dimensional sphere, at least in the topological sense. Okay? So almost surely SD is homeomorphic to the two-dimensional sphere. It's a result that was proved by Le Gall and Paulin, and shortly after I gave an alternative proof for that. And this, of course, justifies calling this random metric space a random surface. Okay? However, this surface has a very rough geometry, and it's very far, for instance, from being a Riemannian structure. And one way to emphasize that is a theorem by Jean-François Le Gall in 2007, showing that the Hausdorff dimension of SD is equal to 4 almost surely. Okay? So of course this property is sometimes very surprising when you see it, but for the first time. But of course you should think of the Brownian map of being an analog object to to Brownian motion. Okay, and that's actually the reason why it's called Brownian map. Okay, and Brownian motion, although it's a continuous path, is very far from being differentiable, and it's known that Brownian motion, the trace of Brownian motion in dimension bigger than or equal to 2, is 2 almost surely. Okay, so it's a path which sort of looks like a two-dimensional object. Here it's a surface which wants to look like a four-dimensional object. Okay, and a way to understand this is that typical points in the Brownian map stand above extremely thin spikes, if you like. You should think of the Brownian map as a kind of ball with a lot of spikes or a lot of mountains on top of it. Okay, and the reason is that, of course, at the tip of a spike, the volume of the balls is typically much smaller than on a flat Euclidean surface, okay, where the radius should be R2. Here at the top of a spike, it turns out to be R to the power 4, which when R is small is much smaller than R2. Okay? Another way to emphasize this roughness of the geometry in the map, and which also connects with the picture of a random mountain area, if you like, is the following property of confluence of geodesic, which was noted by Le Gall in 2010, and which says the following. So you consider a point X, which you want to be somehow typical in the Brownian map. So you pick, if you like, X uniformly at random in the map. So maybe it doesn't make sense because if you have a metric space in general, you cannot, don't always have a notion of a point chosen uniformly at random. But you can think about doing such an operation in the discrete setting, okay, in a discrete random map, which will give you which is always possible, of course, because in this case you have a finite number of vertices, which will give you a space with a marked distinguished point. Okay? And you can think about this marked space to converge to to the Brownian map with a distinguished point. And that's one way to make sense of this. But of course, there are other ways, and in particular, there is a natural probability measure carried by the Brownian map that I'm not going to comment more about. So you take this uniform point, and now you want to consider all the geodesics, all the geodesic paths, so the shortest path from other points, which I call y here, to x. And the property is that if you choose a small radius epsilon, okay, which in this case is a large ball here, you can always find a smaller radius eta here, such that all the geodesics started from points outside the ball of radius epsilon coalesce before coming to x. Okay? And they do so before entering the ball of radius eta about x. Okay? So that means in particular that all the geodesics from points outside of this ball to x have to pass through the point which is here, okay, on the boundary of the ball of radius eta. Which is, of course, a very surprising property of these objects, and in particular, if you want to think about what a typical triangle looks like in the Brownian map, maybe a triangle between 3 points chosen uniformly at random, well, the answer is that this triangle looks something like this. Okay, a triangle made of geodesic arcs, if you like. Okay, it looks something like this. So there are always little common geodesic paths from these 3 points before they branch into two distinct geodesics. Okay, and this, of course, is something that should remind you of what happens in maps, actual geographic maps in mountains, right? When you go from one peak to the other, you first go down in a valley, then maybe paths branch in 2 different valleys, and then they go up in the peaks. You don't, when you are at a peak, you have no choice but to first go down the valley. Okay. And I mentioned that this result has been recently improved in a joint work with Omer Angel and Brett Kolesnik, which says that this confluence of geodesic is also robust with respect to the location of the base point, if you like. So even if you move a little bit the base point x about this typical point, then the geodesics from this new point also will have to pass through this narrow corridor, if you like. And this has some interesting consequences about the Brownian map. Okay, so these are some of the many intriguing properties of the Brownian map that you can find, and in many respects, in fact, there are lots of things that we don't know about the Brownian map. But maybe I'll come back to that later. Okay, I wanted also to mention the problem of universality, because I emphasize universality as one of the most important properties of Brownian motion, and in this context, universality asks whether the limiting space, the Brownian map, depends on the particular choice of approximating spaces that you've chosen, right? Here I've been choosing uniform random quadrangulations, but of course it's very natural to choose, for instance, triangulations. And in fact, in a paper with Jean-François Marquer in 2007, we showed that the first result by Chassin and Schaeffer about typical distances in the map could be generalized to a much larger family of maps, namely the family of Boltzmann distributed random maps, which are defined in terms of, I'm going really quickly here, defined in terms of weights that you put on the faces of the map. If you like, you want to give an energy to each face degree. For instance, face of degree 4 have energy 1, and faces of degree 3 have energy 2. And for a given map, the probability that you choose this map is that it's just a product over all faces of the energies corresponding to these face degrees. Okay? So this is called the Boltzmann distributed map, and we showed that in fact, based on earlier work by Boutier, Di Francesco, Guiter, the result by Chassin and Schaeffer generalized very nicely to these Boltzmann maps. And in fact, much more is true, as it was proved by Le Gars in 2011. And a particular aspect of this result, maybe I'll show a more general result later, is that if you consider a uniform P angulation, meaning a map in which all the faces have degree P, where P is either 3 or an even number bigger than or equal to 4. And consider again this map as a random metric space by rescaling the graph distance by n to the -1/4 times a certain scaling constant. Then the limit as n goes to infinity is always the Brownian map. Okay, of course, if you choose this rescaling constant in the proper way. Okay. And a quick comment about this. So you could ask maybe what happens for p bigger than 4 and odd. And of course, the result is believed to hold, but it's not been proved so far for essentially for what people consider to be technical reasons. But even though the proof is not out yet. Okay, and I should mention that there are extensions of this result to many other families of maps. And maybe in this situation, I want to emphasize, for instance, that if you consider a general map with n edges chosen uniformly at random, then it also converges to the Brownian map after an appropriate renormalization. So it's a result we've been obtaining with Jérémy Bettinelli and Emmanuel Jacob. But there are many other results in this direction. And if you like, the family of the set of families of maps that converge to the Brownian map is an ever growing family. And there are fundamental reasons why you would try to find the greatest possible generality. For instance, I want to mention maybe also this work by Adario Berry and Albank, where they consider triangulations or quadrangulations, so which is covered by this theorem, but with a topological constraint that there are, for instance, no loops or multiple edges. Okay, and this can look like a very innocent generalization, but it's really not. You really need there's really something to be proved. And the interest about this is that simple triangulations and quadrangulations somehow have better embeddings in the sphere. You have distinguished embeddings of such objects. So there are fundamental reasons why you would consider those. Right. Okay, let me also mention another direction to generalize the previous results, which are considering maps not in the sphere but in surfaces with other topologies. Okay, so I want to consider, for instance, here now maps that are quadrangulations on the torus with G handles. Okay, which is essentially all compact orientable surfaces without boundary, which are connected, are of this form, a well-known classification result of surfaces. Okay. And I want these to have, so I didn't say it, I want them to have n faces. And I also want them to be bipartite, which is a kind of technical condition here, where bipartite means that I can color the set of vertices of the quadrangulation in black and white in such a way that two neighboring vertices are always of different colors. Okay? And it's the same to ask that all the cycles in this map have even length. And similarly, you can consider the set of quadrangulations maybe on surfaces which have a boundary. And one way to do that is to consider the set of quadrangulation where all the faces have degree 4 except one distinguished face, for instance, the face incident to the root, which has an even degree which is not fixed. Okay? And you want to consider that as a quadrangulation with a boundary of size 2m. Okay? And so we show in an ongoing joint work with Jérémy Bettinelli that similar results as the previous one holds. Namely, if you rescale the graph distances in a uniform quadrangulations of the G torus with n faces, then it converges to some metric space in the Gromov-Hausdorff distance. And similarly, if you consider a map with a boundary, so maybe I should draw a picture here because if you like, the first result is a discretization of the torus, random discretization by the torus by squares like this. So it converges to some limiting metric space. And for the disk, you should really imagine that the face with degree 2m is an outer face, and inside it's paved by little quadrangles like that. Okay. And of course, in order that this makes sense, for instance, the outer face, you see that you have some freedom here. And for instance, if the outer face has degree 4, then the limiting space here should really be the Brownian map, because a map with a boundary of all faces have degree 4 plus the exterior face, it's also a uniform quadrangulation. So you have some freedom here. And here what you want to do is to have a boundary whose length goes to infinity at the speed at a speed which is given by the square root of the total number of quadrangles. Okay, so you want m over square root of the number of quadrangles to converge to some limiting lambda, a positive and finite number. Okay, in this case, you have convergence to this limiting metric to a limiting metric space. And of course, you want to call that the Brownian torus of genus G, and this the Brownian disk with parameter of boundary size lambda. Okay, because lambda definitely measures in a way the boundary size. Okay. In fact, we have more general results, mixing both, taking several handles and maybe several boundaries, but maybe these are the most important ones here. Okay. And so I should mention that the properties of the limiting space or limiting spaces have been already studied in previous papers by Jérémy Bettinelli. And in particular, this Brownian object is indeed homeomorphic to a torus with G handles, so the topology is preserved. And similarly, this object is also homeomorphic to the disk. And the roughness of the geometry is still something that you see here. So the Hausdorff dimension of these spaces is 4. And in the case of maps with a boundary, the dimension of the boundary is equal to 2. So the boundary, even though it is a curve, has, if you like, same dimension as Brownian motion. Another thing that you could ask is what happens when the lambda is equal to 0 or infinity, corresponding respectively to a very small boundary or a very large boundary. And in the first case, well, if the boundary is too small, then the scaling limit is again the Brownian map, meaning that somehow the exterior face collapses into a point in the limit. And in the second case, things are very different in the sense that the boundary sort of takes over all the geometry of the map. And in this case, if you like, a map with only a boundary and no interior faces, it's really a map with only one face, if you like. So it is really a tree. If you think about it, a tree is nothing but a map with only one face. And in this case, so first of all, the distances do not rescale in the same way as before. They really rescale this time as a square root of the length of the boundary. And the limiting object is an object which is called the Brownian continuum random tree of Aldous. And it's a much older object. It's been introduced in the 90s. And it's a very famous object that, in fact, plays a prominent role in the study of these random metric spaces here. Okay. You could, in fact, ask about other kind of renormalizations here. And in fact, interesting things happen, but I'm not going to talk about that here. Instead, I should maybe talk a little bit about the methods that you have at your disposal to prove such results. And something that is really recurrent in this topic is the word bijection. So in fact, it is always extremely useful to rely on bijective approaches for the enumeration of maps. And this is really a study that has been initiated at the beginning of the 80s by Corey and Vauquelin, and later Arques, and much later, in fact, Schaeffer at the end of the 90s. And since the work of Schaeffer, it has, in fact, many other contributors. And what do these bijective representations do? Well, first of all, they want to give nice explanations for the very simple formulas for the enumeration of maps that I've, one of which I've been emphasizing earlier on. The number of maps with n edges is, some prefactor times the number of trees, of plane trees. Okay. So of course you want to have an explanation for this, and that's the first, maybe the first motivation. And another motivation is that, in fact, usually when you find a nice bijection, you also have with this bijection some nice properties of the objects that you want to study. As soon as, of course, the bijection involves objects that are simpler than the one you started from. Okay? And in fact, all these bijective techniques rely on the same kind of vague ingredient, which is which is a representation of the map that you consider, or some variation of the map, as a gluing of two objects, which are a spanning tree drawn on the map and the dual spanning tree of this map. Okay, and if you want all the bijections for all the nice bijections for map, they use this idea in a certain way. The idea is that depending on the problem that you are considering, you might want to choose this pair of trees, let's say the primal tree or the dual spanning tree, in a different fashion. And for the problem that we want to consider here, which are graph distances on uniform quadrangulation, say, what you want to do is to consider a spanning tree which reflects the properties of the geodesics or the geodesic distances in the map. So what Corey-Vauquelin did, maybe not by stating things in this way, was to use a depth-first exploration of the geodesic path from the root of the map. Okay? So if you like, in doing so, you decompose the map, or you decompose the geodesics of the map into a kind of spanning tree made of geodesic paths. Okay? And then the dual spanning tree, which you can call the discrete cut locus, which is the set of points which can be attained by different, at least two distinct geodesics, turns out to have the fantastic property, which is not at all obvious here, to be unbiased in the family of plane trees. Namely, if you choose a uniform random quadrangulation and perform this depth-first exploration of geodesics and pass to the dual tree, then the dual tree is a uniform tree in the family of plane trees. Okay? Of course, in saying that, I'm being extremely vague, and in fact, I cheat a little bit when I say that. But that's really the idea. And if you like, this this unbiased choice comes really from the fact that in the enumerative formula, you saw appearing this Catalan number. And in fact, this Catalan number exactly enumerates the objects which are the discrete cut locus, which appear in this depth-first exploration of geodesics in the tree. Okay. And then, once you have these bijections, well, you can rely on prior knowledge of scaling limits for random trees, and in particular, in the 90s, Aldous has developed a very nice theory about scaling limits of discrete and continuum discrete trees to continuum objects. We've already seen the Brownian continuum tree in the context of maps with a boundary, and also Le Gal's Brownian snake, which is an elaboration, if you like, on this, where you also endow the tree with labels. And in fact, this elaboration, putting labels on the Brownian tree, allow to recover the pair of trees before. Not only the dual tree is necessary, of course, to reconstruct the map, but you also need more information. Okay? And the idea is that the exact information that you need, in fact, is in say Aldous and Le Gal's study of scaling limits of trees or labeled trees. Okay. So a bit later, I don't know if I will have time for this, we will consider other models of maps, which are maps which are decorated with models of statistical physics. And for those maps, you also have nice bijections. So Scott Sheffield, in fact, has found a very nice way to describe them based on earlier work, in particular by Olivier Bernardi, which also describes the maps in terms of a pair of tree and dual tree connected together. And it turns out that when you study this tree, you obtain an information which is completely different from the information of the distance. You obtain more properties on the, on the model that you have chosen on the map. Okay, and there are very interesting open questions related to this problem. So the idea here is that the fact that we are able to find the scaling limits for the graph distances really relies on a kind of a miracle from this bijection, which is that when you perform this exploration of geodesics, the trees that you obtain have a very simple distribution, okay, which is not at all the case in other situations. Okay, so in the remaining time, I want to talk about other aspects of the theory of random maps and move a little bit away from the problem of scaling limits for a second. So I should mention that in 2002, in fact, almost simultaneously to this study by Chassin and Schaeffer that I mentioned earlier, there was a very important paper by Angel and Schramm, followed shortly after by another paper by Angel, considering local limits result for random triangulations. So in a local limit problem, what you do is instead of rescaling the maps, instead of rescaling the graph distance by some factor tending to 0 in order to observe a continuum object in the limit, what you do is you don't rescale the distances at all. Okay, so you leave the edges, you really leave the edges be, okay, they still remain there with a length 1, if you like. And what you do is you consider, so it's sometimes called the Benjamini-Schramm topology, you consider that two maps are going to be close from one another if they coincide in a large but fixed neighborhood about their roots. Okay, so it's a kind of, if you like, a myopic view of the map. You will, for instance, a very French way to say that is that if you live in Paris, well, Paris is a very good approximation of France, if you like. Yeah. So many people who live in Paris, and I was born in Paris, so but now I live in another city, so I was proved wrong, maybe, I don't know. So really, you will consider, for instance, that the red map here is a very good, let's imagine that this map is a ball of radius 2 about this point here, okay? You consider that this map is a good approximation of the infinite map of any completion of this ball up to level 2, okay? And the distance, if you like, between two maps will be 1 over the maximal ball in which these two maps coincide, okay? Okay, so using this topology, Angel and Schramm built, the limiting objects for uniform. In fact, they studied triangulations, but there is really nothing very special to triangulation. It makes things a little bit easier in this context. And later, Krikun also considered the analog uniform infinite planar quadrangulation. So it's really a limit, a local limit, as n goes to infinity of a uniform triangulation or quadrangulation. So you should think about it as an infinite graph, okay, made of triangles, and it's really a graph now drawn on the plane. Okay, it has, if you like, no accumulation point on the plane. It's really the random lattice of the plane made of triangles. Okay. I mentioned also that work by Chassin-Durus and later Ménard also generalized the bijective approaches to this context. So here are some aspects of local limits that are very important. They actually turn out to meet also the problem of scaling limits. So one very important property of these local limits is that they enjoy a so-called domain Markov property. Okay, so it was noticed by Angel Schramm, and then later this paper by Angel, and then systematically studied in this paper by Angel and Rai. And so this domain Markov property is easier to present in a context of random maps drawn in the half plane rather than the plane. So you should imagine this line here as being the boundary of an infinite triangulation that is drawn on the top half here. Okay, here you have nothing below. Okay, and you want to consider somehow this map to be unknown to you. You just see the boundary, and you want to reveal this map step by step, if you like. So what you do is you reveal the triangle which is incident to the root, and this triangle has two possible shapes. Either it's incident to a vertex which lies inside of this unknown region, or the third vertex also lies on the boundary. And in this case, it will cut the map into an infinite part and a finite part. And the very important domain Markov property here is that in all cases, conditionally on either this or this event to happen, the infinite part has a law which is equal to the initial law of the uniform, of the initial map. Okay? So again, you have a random map here. Okay? You reveal the triangle which is here, and the law of what remains is the same as the law of the total map. Okay? And here it's the same. Okay. Of course, the boundary is modified, but it always looks the same as before, if you like. It's always an infinite, a doubly infinite chain of vertices. And there are, of course, versions of this domain Markov properties in the context of the full plane maps, but it's slightly more complicated to state. And this domain Markov property is also a very powerful object, which is kind of dual, if you like, to the study of these geodesic trees, if you like. And they are in certain aspects, certain respects, sorry, they are more flexible. And notably, what you can do is study using this Markov property the volume growth of the metric balls in the graph metric. And this was done by Angel. And this was actually the first time where it was understood that balls in these random lattices with radius r grow like r to the power 4. It was really the first time where this exponent 4 appeared, which is of course related to the Hausdorff dimension. And also a very nice result by Angel is that using these constructions you can also find explicitly the critical percolation threshold for the percolation on these models. And I've cited a number of works in this topic. So it's really a powerful construction that allows you to study several properties of these geometries. Now I wanted to mention another fact which sort of parallels the fact that the Brownian map has a very rough geometry. Again, here it's not at all like the Brownian map. It's really an infinite but discrete graph. But still, you can see that the geometry of this graph is quite rough in the following sense. This is a result by Curien, Ménard, and myself, where we prove that in this infinite uniform plane quadrangulation, there exists an infinite sequence of vertices P1, P2, and so on, such that any infinite geodesic path, so a path which is a geodesic is just a path in which it's a path drawn on the graph, started at some point, say V0, okay, such that the distance, the graph distance between Vi and Vj is equal to I minus j. Okay, so it's really a shortest path, if you like, from any point on this path to any other one. Okay, and you consider all the infinite geodesic paths. Okay, and it turns out that all these paths, they will go through all of these vertices P1, P2, except maybe a finite number of them. Okay, so if you want, it's really related to this confluence of geodesic. Wherever the geodesic starts, they will want at some point to pass to some point of this infinite collection. Of course, if you take a point which is very away from this point, it will not pass through this particular point, but later it will catch up this family of points Pi. And you can restate it in a slightly different way, because one consequence of that is if you fix two vertices x and y, then the function which takes the graph distance from x to z minus the graph distance from y to z, where z is the parameter of the function, this function is in fact almost constant, meaning for z, which is in the complement of a large ball, this function will always be the same. And this, you can interpret that in geometric terms by saying that there is a unique point at infinity in the so-called Gromov compactification of the UIPQ. Well, it's not unique because you can remove P2 and you will obtain another such. Yeah. Well, there is, if you like, it's unique if you ask that this sequence is maximal, if you like, but it's not really important. I mean, it's unique in the sense that if you take two such sequences, there will be an infinite number of common elements to these two sequences. Okay. So maybe I want to finish with the initial motivation from theoretical physics for these problems and maybe some perspectives. So I don't know, maybe I have 5 more minutes. We started a bit late, so. Okay. So as I said earlier, we want to see maps as discretized, if you like, Riemannian manifolds. Okay? And the original motivation for that came from the theoretical physics literature in the early 80s, namely the theory of so-called two-dimensional quantum gravity, in which you want to consider a fluctuating, if you like, a fluctuating space-time, so a fluctuating geometry. So of course, quantum gravity is really something that is supposed to, it's a theory that is supposed to hold, if you like, in a 4-dimensional space or a 3 + 1 time direction dimensional space. But already, this kind of simpler situation where you consider just 2 dimensions of space is quite interesting. And in this theory, you again want to consider, if you like, a uniform measure on metrics, or maybe a simpler object, which is a so-called partition function, which is an integral over all Riemannian metrics on a given manifold M of dimension 2, of the exponential of minus the area of M with respect to this metric G. And again, G should be chosen according to a kind of Lebesgue measure, if you like. And this measure should be invariant by, if you like, reparametrization of the surface, namely the action of the orientation-preserving diffeomorphisms on the Riemannian metrics. Okay, so this is sort of one of the basic objects of two-dimensional quantum gravity. And of course, the problematic object is really this dg bracket here. Okay, the bracket is here to account for the quotient, and the dg should be somehow the uniform invariant or equivariant, I don't know, measure on Riemannian metrics. Okay, and the approach that we've been discussing so far, the discretization approach, was initiated by, in fact, Weingarten and then many people. So I've listed some of them, but probably not all of them here. Probably forgot to state Polyakov as well. Is to replace this ill-defined integral by this well-defined sum over triangulations. Okay, you replace the metrics, the continuum metrics, by discrete metrics. So this is really what we've been doing. Okay, and the program now is to take scaling limits and obtain the Brownian map, if you like. This is really going the other way somehow. Okay. Okay. So I mentioned that one of the success, the historical success, if you like, of this approach is that this is very well connected to the enumerating theory of maps, in particular to the matrix the relation with matrix integrals, which has a huge number of entries in the physics literature in particular. Okay, and I mentioned again that this metric aspects have been really obtained using a different approach, which are bijective approaches. In fact, in the recent literature, it was shown that some of the early attempts, in particular by Ambjorn and Watabiki, of using matrix integrals to find random distances in maps, in fact, can be made rigorous. And there is, in particular, a very nice paper by Ambjorn and Budd that I didn't cite here, but which sort of makes the link between the two. Now there is a completely different approach to making sense of this integral, which is a purely continuum approach, which is called the Liouville theory approach, or quantum Liouville theory approach. And the idea is sort of to perform a change of variable by saying that a metric in 2 dimensions is given by a simple formula. So if you are on the sphere, the formula is very simple. You fix a given metric on the sphere, for instance, the usual, usual Euclidean metric or intrinsic Euclidean metric. And now any metric can be obtained from that by multiplying by a conformal factor, e to the 2u, where u is a certain function. And if you perform a formal change of variables going from Riemannian metrics to this conformal factor, then you can argue that U should be a Gaussian random field. And this random field, unfortunately, should not be a smooth random field, but rather a distribution-valued random field called the Gaussian free field. And it was made, the problem here is that, first of all, if U now is a very rough object, like a distribution, first of all, it doesn't quite make sense to consider the exponential of this distribution. And second, it doesn't really make sense, then even though you can sort of make sense of this object in a certain way, it's not clear what the new metric should be. You know, you cannot really, for instance, integrate this metric along curves. In fact, it was shown in 2008 by Duplantier and Sheffield how to make sense of the measure which is associated with this metric. So not the metric, but rather, if you like, the determinant of the metric tensor times dz, where dz is the area measure. And this measure is very closely related to Kahan's Gaussian multiplicative chaos theory. Okay, and in fact, a lot of work in these topics. And this was an important fact because it gave the first explanation of, of a deep correspondence in the theoretical physics between fractal dimensions of random sets measured with respect to the Euclidean distance and measured with respect to this quantum sort of metric here. It's called the KPZ relation, and it's still in many respects a kind of mysterious relation. I should mention here before stopping that there are more recent advances on this problem. In particular, so Garban, Ronan Vargas, and also Berezkiki in independent works introduced if you like, a natural diffusion on this metric. And they were able to do this by using, the very powerful property of Brownian motion, which is the conformal invariance. And somehow by deciding that Brownian motion inside this metric should be conformally invariant, there is a very natural candidate for it, and they call that Liouville-Brownian motion. And there is a hope that this Liouville-Brownian motion can be sort of used to probe the metric. Even though the metric is not defined, you know what the diffusion in this metric should look like. And a very recent progress by Miller and Sheffield was done by introducing a family of objects called the QLE with two parameters, of which a particular member, so these QLEs are objects that are random growth processes coupled in a certain way with the Gaussian free field. And it's believed that this QLE with a very particular specification of the parameters is the right object to describe the growth process of the metric balls of Liouville quantum gravity. And okay, maybe I should have written that here, but this is supposed to be really the balls in the Brownian map. Okay, so there is a strong hope that in a short amount of time there will be a direct connection or direct construction of the Brownian map using objects such as the Gaussian free field. Okay, so maybe before stopping, I will skip on this last part. I wanted to mention other developments. So far I've been considering only maps, which just somehow live by themselves. You choose a uniform random quadrangulation or a uniform random triangulation. But again, you can consider maps coupled with statistical physics models. For instance, the Ising model, percolation, self-avoiding walk, or more general models. And a particularly attractive model in this context is the so-called random cluster model, or FK percolation on a random graph. And it turns out that, as I mentioned earlier, there is also a natural way to describe these FK percolation configurations bijectively as a pair of trees, let's say primal tree and dual tree, glued together on top of a map. Okay? And it's a method that's bijection that is due to Sheffield. And a very recent work by Duplantier, Miller, and Sheffield draws a link between these maps and couplings of the GFF, the Gaussian free field, with the random curve known as SL. Okay, and so Okay, we need more time to comment on this, the notion of topology that they use, but I think that the catch here is that it stresses how these couplings between Gaussian free field and SLE can be understood, you know, in the continuum as the continuous analog of this representation of maps as gluings of two trees together. Okay, and in the continuum, it's called the mating of trees, which is something which is quite familiar, very familiar to people who do, in particular, dynamics, complex dynamics. Okay. And maybe I'll stop with one important question, which is that, so even though you have these you know, these nice descriptions of maps with statistical physics models, you know, either in the discrete by discrete mating of trees or in the continuum, there is nothing really known about the typical graph distances in these maps, except in the trivial cases where there is no statistical physics models, okay, or in the case where these statistical physics models are decoupled, like percolation. In this case, you know, maybe the main question in this topic is, let's take a map with an Ising model coupled on top of the map, take two uniformly chosen points. What is the order of the distance between these 2 points in terms of the total number of quadrangles in the map, or the number of faces in the map? Okay? And this is completely unknown, and it's also subject to controversy in the physics literature. It's related to a prediction by Watabiki that he did. There is no, at the moment, no strong support either to this conjecture formula or that this formula does not hold. It's really something that is quite unsettled. Okay, and I think that will be all for today. Thanks for your attention. Any questions?
You had a beautiful picture before. Was it?
Yes. So it's okay. So I wanted to comment a little bit more on these statistical physics models coupled with maps, and so of course there is so this recent work by you and Miller and Sheffield, and this is a kind of different approach to it, which is a work we've been. It's based partly on the work we've been doing with Jean-François Le Gall on the so-called stable maps, which are maps that you obtain when you consider, so when you have the statistical physics models on top of maps, you can consider, for instance, interfaces linked to these models. And then you can empty the interior of the interfaces. And it turns out that you obtain nice models of maps, which are maps with large faces. And with Jean-François Le Gall, we studied the scaling limits of such objects. And this diagram makes a link, if you like, between these objects and a study by Borot, Boutier, and Guiter that they did for, in particular, well, actually they also studied the FK percolation model, but with a very different approach than using the Sheffield bijection. But using this Borot, Boutier, and Guiter results on the partition functions of, in this case, ON models for random maps, we were able to make a link with our study of stable maps. And this picture here are, if you like, a picture about the conjecture, the geometry of the stable maps. In certain phases, the stable maps look like these like Sierpinski carpets, and in other phases, they have this structure of gasket structure with local cut points. That's what the picture is about. But we would need at least 10 minutes to comment more.
Earlier, you discussed some properties of these Brownian maps, yes? And there was one property where you had epsilon and eta.
Yes.
Do you know what is the typical behavior of eta as function of epsilon?
Let's see. So there is no unfortunately, there is no uniform, if you choose the point if you choose a point in the map in a non-careful way, the eta could be extremely small, if you like. There is no lower bound, and for instance, you see immediately that this cannot be uniform in any way, because if you choose the base point in the middle of a geodesic, you see that there is the property of confluence of geodesic does not hold. So you can think that for points that are very close to this point on a geodesic, this property will also decay, if you like. So there is no, at least to my understanding, that there is no nice way to say, okay, eta is of order epsilon to this power. It's not something that is going to be uniform in the map. Yeah. But of course, it's important still to know what are the good points, for this confluence of geodesics, if you like, and what are the bad points for that. That's that's a very interesting topic, in fact, studying the fine structure of the geodesic network, if you like, in the Brownian map.
There's no more questions. I suggest we thank Grégory again.
Thank you.